Golden Iris Productions presents The Hidden Rhythms of the Hydrogen Atom, Wave Structure, Quantized Motion and Photon Emission by Mark F. Dennis.
Part 2.
Abstract. The development of modern atomic physics emerged from a sequence of foundational discoveries spanning the electron, proton, quantized radiation and matter-wave duality. Beginning with the identification of subatomic structure by J. Thomson and Ernest Rutherford, and culminating in Bohr's quantized atomic model, a new framework of discrete energy states replaced the classical continuous description of matter. Concurrently, Planck's resolution of the ultraviolet catastrophe introduced energy quantization through E equals h nu, later extended by Einstein's photon hypothesis, establishing the quantum nature of electromagnetic radiation. De Broglie's matter-wave theory further unified these developments by proposing that all matter exhibits wave-like behavior governed by lambda equals h over p. This work presents a consolidated historical and theoretical foundation of quantized atomic structure, emphasizing the emergence of discrete electron shells, standing wave conditions, and photon emission as interconnected consequences of wave-particle duality.
Introduction. The discovery of the electron by J. Thomson and the subsequent identification of the proton through the work of Ernest Rutherford fundamentally transformed the understanding of atomic structure and established the foundation of modern atomic physics. Prior to these discoveries, the atom was widely regarded as an indivisible unit of matter. However, experimental evidence demonstrated that atoms possess an internal structure composed of charged constituents. Building upon this framework, Niels Bohr proposed his atomic model in 1913, introducing the revolutionary concept that electrons occupy discrete, quantized orbits around the nucleus. Within this model, electrons may transition between allowed energy levels, emitting or absorbing electromagnetic radiation, whose energy corresponds exactly to the difference between initial and final states. This provided the first successful theoretical explanation for the discrete spectral lines observed in hydrogen, and established that light emission from atoms is a quantized process rather than a continuous classical phenomenon. At approximately the same time, classical physics encountered a fundamental crisis in the form of blackbody radiation, known as the ultraviolet catastrophe. Classical theory predicted that a heated object should emit infinite energy at short wavelengths, a physically impossible result. In 1900, Max Planck resolved this paradox by proposing that electromagnetic energy is exchanged in discrete packets, or quanta, with energy proportional to frequency, E equals h nu, where h is Planck's constant, a fundamental constant of quantum mechanics. This result demonstrated that energy is not continuously divisible, but instead exists in discrete units.
Planck's hypothesis unexpectedly revived aspects of Isaac Newton's earlier corpuscular theory of light. Although wave theory had been firmly established in the 19th century through the work of Thomas Young and James Clerk Maxwell, Planck's quantization suggested that electromagnetic radiation also exhibits particle-like behavior. This duality was confirmed by Albert Einstein in 1905 through his explanation of the photoelectric effect, in which light is treated as discrete localized quanta, later termed photons. This established that electromagnetic radiation is neither purely wave nor purely particle, but fundamentally quantum in nature. Together, Bohr's atomic model and Planck's quantum hypothesis revealed that light is produced through discrete electron transitions governed by quantized energy exchange. This marked the beginning of quantum theory and fundamentally reshaped the understanding of physical reality. With light now understood to exhibit both wave-like and particle-like properties, physics entered a deeper conceptual transition. In 1924, Louis de Broglie extended wave-particle duality by proposing that matter, previously considered purely particulate, also possesses wave-like properties. This hypothesis is expressed by the relation lambda equals h over p, where the wavelength lambda of a particle is determined by its momentum p and Planck's constant h.
This proposal implied that every moving particle is associated with a wave, and for the electron, this wave-like behavior provided a natural explanation for the quantized orbital structure first introduced by Bohr. The Bohr model had already demonstrated that electrons in the hydrogen atom occupy discrete energy levels, or shells, labelled by the principal quantum number n. Each value of n corresponds to a specific allowed orbital radius. The ground state, n equals 1, defines the Bohr radius, A0, approximately 5.29 times 10 to the minus 11 meters, which sets the fundamental scale of atomic structure. Higher shells follow the relationship R sub n equals n squared A0, demonstrating that orbital radii increase rapidly with increasing quantum number.
What Bohr introduced as a postulate finds a physical interpretation through de Broglie's wave mechanics. The electron is permitted to occupy only those orbits in which its matter wave forms a standing wave around the orbital circumference. This condition requires constructive interference, expressed as 2 pi Rn equals n lambda n, ensuring that only integer wavelengths fit around the orbit. If this condition is not satisfied, destructive interference prevents stable orbital formation.
In this way, quantization merges naturally from wave behavior, rather than being imposed as an independent rule. This wave-based interpretation unifies Bohr's atomic model, Planck's energy quantization, and Einstein's photon concept into a single coherent framework. When an electron transitions from a higher to a lower energy level, its standing wave configuration changes, and the resulting energy difference is emitted as a photon, governed by E equals h nu. In this formulation, light arises from the reconfiguration of stable matter wave states. The hydrogen atom, therefore, represents the first physical system to demonstrate that matter and radiation are governed by the same underlying quantum principles, in which discrete atomic structure and discrete light emission are two manifestations of wave-particle duality. De Broglie matter waves and the emergence of standing wave quantization. Most importantly, the quantized velocities derived in the previous section define discrete kinetic energies for each allowed electron shell. When the electron transitions from a higher velocity orbit to a lower one, the difference in total orbital energy is released in the form of electromagnetic radiation. In this interpretation, photon emission is not an independent process, but a direct consequence of changes in the electron's velocity, acceleration, and underlying wave state configuration. Thus, the light emitted by hydrogen is not arbitrary, but arises from precise differences between quantized dynamical states. Each photon carries the exact energy corresponding to the transition between two allowed electron configurations, making radiation the observable signature of quantized motion within the atom. Matter wave wavelength of the electron. With discrete velocities established for each shell,
Louis de Broglie's matter wave hypothesis provides a direct connection between particle motion and wave structure. The associated wavelength is given by lambda equals h over mev, where h is Planck's constant, me is the electron mass, and v is the orbital velocity. Substituting the ground state velocity at the Bohr radius yields a wavelength of approximately lambda 1 equals 3.33 times 10 to the negative 10 meters. This value is equal to the circumference of the Bohr orbit, indicating that the electron exists in a fundamental standing wave configuration at the ground state. This result is not coincidental, but instead represents the first direct evidence that atomic orbits correspond to wave resonance conditions, standing wave condition, and shell quantization. The physical interpretation of Bohr's quantized shells follows directly from the requirement that the electron's matter wave form a stable standing wave around the nucleus. This condition is expressed as 2 pi Rn equals n lambda n, where n is the principal quantum number. This condition implies that only orbits in which an integer number of wavelengths fits around the circumference are permitted. Specifically, n equals 1, one wavelength fits the orbit. N equals 2, two wavelengths fit the orbit. N equals 3, three wavelengths fit the orbit. Higher n, integer multiples of the fundamental wavelength. This produces the sequence of de Broglie wavelengths, lambda 1 approximately 3.33 times 10 to the minus 10 meters, lambda 2 approximately 6.65 times 10 to the minus 10 meters, lambda 3 approximately 9.98 times 10 to the minus 10 meters, and so on for higher shell.
Scaling relations and structural symmetry. This wave-based formulation reveals a fundamental symmetry in the hydrogen atom. While orbital radii increase according to Rn equals n squared, a0, the electron velocity decreases inversely with the principal quantum number, Vn equals V1 divided by n. As a direct consequence of the de Broglie relation, the wavelength increases linearly with n, lambda n equals n lambda 1. This establishes a consistent scaling hierarchy linking spatial structure, dynamical motion, and wave behavior within the atom. Each successive shell corresponds to a larger, lower energy standing wave mode of the electron.
Unification of orbital motion and wave resonance. The relationships above demonstrate that the structure of the hydrogen atom emerges naturally from wave resonance conditions rather than being imposed as an independent quantization rule. The allowed radii, velocities, and wavelengths are mutually constrained by the requirement that the electron's matter wave maintain constructive interference around the orbit. In this formulation, Bohr's quantized shells, de Broglie's matter waves, and classical orbital motion converge into a single consistent description of atomic structure as a standing wave system.
Wave unification and conceptual completion of atomic quantization. This relationship unifies Bohr's quantized shell structure into a single wave-based framework. Each higher energy level corresponds to a higher order standing wave harmonic of the ground state configuration. In this interpretation, the hydrogen atom behaves as a resonant cavity in which the electron is restricted to configurations satisfying exact wave resonance conditions.
This reformulation transforms Bohr's atomic model from a phenomenological postulate into a physically grounded wave system. What Bohr introduced as discrete allowed orbits is naturally derived from de Broglie's matter-wave hypothesis, in which the quantized radii, velocities and energies emerge as direct consequences of standing wave boundary conditions.
Ununification of light and matter. This framework completes the connection between light and matter. Planck established that electromagnetic radiation is emitted in discrete quanta. Einstein demonstrated that these quanta behave as localized particles, photons. De Broglie extended this duality by showing that matter itself exhibits wave-like behavior. Together, these developments establish wave-particle duality as a fundamental principle of nature. Within this framework, the hydrogen atom becomes the first system in which atomic structure is fully governed by resonance conditions, and in which electromagnetic radiation arises from transitions between discrete matter-wave states. When the electron transitions between allowed shells, the change in standing wave configuration produces a photon whose energy corresponds exactly to the difference between these states.
Physical interpretation of electron quantization. Prior to de Broglie's hypothesis, the electron was treated as a localized particle orbiting the nucleus under Coulomb attraction, analogous to a classical planetary system. While Bohr's model successfully reproduced the observed spectral lines and energy levels, it did not explain the physical origin of quantization. De Broglie resolved this by introducing an intrinsic wavelength associated with matter, transforming the electron from a purely point-like object into a quantum wave entity. In this description, the electron exists as a standing wave distributed along the orbital path, rather than as a localized classical particle. The orbital structure is therefore determined by resonance. Stability occurs only when the electron's wavelength satisfies a constructive interference condition around the nucleus. If this condition is not met, destructive interference prevents stable orbital formation. Thus, quantized orbits emerge as the only allowed standing wave solutions of the system.
Wave-particle duality of the electron. This interpretation reveals that matter at the atomic scale cannot be described adequately using classical intuition alone. The electron exhibits both localized and delocalized behavior simultaneously. As a particle, it carries well-defined mass, charge, and momentum, enabling discrete interactions with electromagnetic fields. As a wave, it extends over space, exhibits interference, and is restricted to resonant states determined by boundary conditions. These two descriptions are not contradictory, but complementary representations of a single underlying quantum entity. The electron is neither exclusively a particle nor exclusively a wave. Rather, it is fundamentally a quantum object whose observed behavior depends on the measurement context. Hydrogen atom as a resonant quantum system. The hydrogen atom provides the clearest realization of this duality. Its discrete energy levels correspond to particle-like orbital structure, while its de Broglie wavelengths describe wave-like resonance conditions. The orbital velocities derived from classical mechanics simultaneously determine matter-wave wavelengths through Planck's constant. During electronic transitions between shells, the system emits photons as discrete quanta of electromagnetic radiation. These photons also propagate as waves, reinforcing the dual wave-particle nature of radiation itself. Thus, both matter and light are governed by the same underlying principle. physical reality is structured through quantized resonant states that manifest in both wave and particle form.
Completion of the quantum conceptual framework. De Broglie's matter wave hypothesis completes the conceptual transition initiated by Planck and Einstein. It unifies Bohr's atomic structure, Planck's energy quantization, and Einstein's photon hypothesis into a single coherent framework. This synthesis forms the foundation of wave mechanics and the later formal development of quantum theory by Schrödinger and Heisenberg. Within this framework, the electron is understood as a quantum entity defined by the harmony between wave structure and particle-like localization, rather than as either independently.
Transition to relativistic structure. During the early 20th century, while quantum theory was emerging, Albert Einstein was developing a fundamentally different but equally revolutionary framework, general relativity. Einstein sought to describe gravity not as a force acting at a distance, as in Newtonian mechanics, but as a manifestation of space-time curvature induced by mass and energy. The mathematical formulation of this theory required an entirely new description of geometry and dynamics, and its development occupied Einstein for several years during World War I. At the same time, Karl Schwarzschild, serving on the front lines of the war, obtained Einstein's field equations and derived the first exact solution for a spherically symmetric, non-rotating mass. Despite the extreme conditions of his service, Schwarzschild successfully obtained a complete analytical solution and transmitted it to Einstein, who was reportedly astonished by the result.
To be continued.